I was expecting
We should start. Good morning, everyone, and welcome to the 2025 Cheriton Symposium. I should say this is the best event of the year for me, and because it brings us together as a school, including alumni, retirees, student faculty, staff, and students to celebrate research excellence. So this year, Symposium is a special one because it marks the 20th anniversary of the transformative investment David made in the school that now bears his name. I looked up the news archive of the university and found in the November 2005 daily bulletin an announcement of David investment, and when David was asked why he made this investment, I'm going to quote you, David.
What did I say?
Says, URLU was a transformational experience for me, taking me from a naive undergraduate to the leading edge of computing research and providing the basis for my career. More personally, I treasured the friends I made at Waterloo and fond memories of those times. I am delighted to be in a position to give back to Waterloo and excited by what this gift may enable, building on Waterloo's strong faculty, students, and reputation. Education is the best investment one can make, as I thankfully figured out early on. So 2 decades later, we continue to see the lasting impact of David's vision. His investment into the school allowed us to recruit 2 Cheriton chairs, 6 faculty fellows, and thousands of graduate student scholarship each year. Today's program reflects this legacy, and this morning we will hear from 3 of our distinguished faculty members, Shane McIntosh, the Ross and Muriel Cheriton Faculty Fellow, Toshiya Hachisuka, Cheriton Faculty Fellow, and Greg Kaplan, the Marston Fellow. Shane is an associate professor and leader of the Software Rebels lab, the Software Repository Excavation and Build Engineering Lab. He joined us in 2020 after serving as the Canada Research Chair in Software Build Automation and an assistant professor at McGill University. He uses empirical methods to study and improve software build systems, DevOps pipelines, developer experience platforms, and software quality. And Shane will speak about continuous integration and delivery pipelines today. Next, we hear from Toshiya Hachisuka. His research focuses on the numerical and mathematical aspects of computer graphics. Combining applied math, CS, and physics, Toshiya works on problems related to visual simulations of objects. He is a member of 3 research groups: for computer graphics, scientific computation, and computational mathematics. Before joining Waterloo in 2020, he was an associate professor at the University of Tokyo, and before that, an assistant professor at Aarhus University in Denmark. And Toshiya will speak about applying Monte Carlo methods to solve partial differential equations. So our third presentation is by Greg Kaplan, a professor in the computer graphics group. Greg studies the application of computer graphics and math to problems in art, architecture, and design. And he's an expert on topics such as Islamic geometric patterns and computational applications in tiling theory. He's a member of the board of the Bridges organization and helps run their annual conference on math and art. As you will learn this morning, Greg was part of the team that discovered the world's first periodic monotiles back in 2023, a discovery and proof that captured the imagination of the public and mathematicians around the globe. After Greg talks, as usual, we'll have lunch in the fishbowl, and then will be followed by a poster session in the DC atrium featuring research from exceptional graduate students supported by the scholarship. Well, enjoy the presentations this morning and take the opportunity to engage with students in the afternoon. The symposium will conclude, again as usual, with an award ceremony in the fishbowl to recognize the top poster presenters. I invite you all, of course, to attend that. And now I will pass the mic to Shane.
Switch this thing on. You should hear me. Yes? We're good? Okay. Thanks, Ro, for the introduction. Like he said, my name's Shane McIntosh. I'm an associate professor here. And today I'm going to talk to you a little bit about some of our research on CI/CD pipelines, specifically focusing on the mess that they generate for developers. So let's imagine that this handsome, brilliant young mind here is a software developer. I know it's a leap, but follow me along, okay? So he might be tasked with fixing an issue. So an issue report's going to describe either a problem with the software or a new feature that we want to develop. He's going to apply his brilliant mind to develop changes to the source code that implement that change. And his first challenge in the modern development cycle is to get that change into a central repository. So we'll call this the integration stage. And after that's done, it's very common in modern settings for automation to kick in. So it's going to download the change and automatically build it. So that's going to transform it from source code into the expected format that will run on the target platforms. And after that transformation, we might run some automated tests to make sure that he hasn't introduced any problems. And since he's so handsome and intelligent, you can see from the green check marks here that, of course, his change cleanly passes and integrates smoothly. Usually after this stage is when we would hand off to a different set of team members with different expertise. So this left side of the figure is the development side, and then traditionally the right side of the figure is the operations side. And operations would download this updated version of the system. They would encrypt it to make sure it's safe and signed carefully and ready for release. Then they would upload that package to a deployment platform. So modern ones might be something like the App Store that you use to install apps. It might be a targeted web server where the website is hosted, and they would deploy the application there. After deployment, they would perform some clever tricks to operate the release. So they might deploy the release so that only people in this room see the new version and everybody else sees the old one. And they might monitor that behavior to see, is the release safe? Like, are the people in this room screaming on social media that the application doesn't work? If not, maybe it's safe and we can roll it out further. Also, during that monitoring phase, you might generate new ideas for how to update the system and make it even better. And those might produce new issue reports that our team can then start to work on. So you might have seen this figure in some form or another. They often refer to this as the DevOps lifecycle. Now, where does CI/CD fit into this? So often when developers make a change, they want quick feedback about whether it's safe to integrate. And if we add a little reporting stage after test here, we would call this a continuous integration cycle. So every time a new change appears, it's automatically downloaded and built, and a report is generated for the team to know if it's safe. If we continue that automation, and if the change has passed CI, we can automatically release safe changes to enable our team to move really fast, right? So you might have heard that modern web applications will release several times per day, and that's made possible by this continuous delivery part of the pipeline. So when I say CI/CD, I'm talking about these two phases. Now, you may have heard about fancy terms like A/B testing or canary releases. That's made possible by automating all the way out to this phase, and we would call this a continuous experimentation lifecycle, where Every change can be formulated as a controlled experiment. So instead of thinking of it as fixing a bug, I could say my hypothesis when making this change is that the crashes that we're observing with this particular type will no longer appear. And then I can make the deployment. I can split my users into 2 groups, just like we would with a medical drug trial. And I can give one group my treatment, the fix, and the other group gets no treatment, and I might be able to evaluate whether my hypothesis, it holds or not. And we would call that the continuous experimentation life cycle. Okay, so if we cut this cycle and we kind of lay it out like a series of stages, right? It's a little easier to digest this way, where we start with planning and we end in the monitoring phase. What my group tends to focus on is this central part. We focus on the CI and CD part of this life cycle. And you might think of it as, at a very high level of abstraction, we take change sets, this summary of the changes that developers have implemented to fix bugs or add features, and we take a set of configuration settings that describe how the build phase performs, how the test phase performs, et cetera. And it produces new releases and reports demonstrating whether the change sets are safe or not. Okay? Now, why do we focus here? Well, look at how happy these stock image people are. When you get this pipeline done very well, it has this amplifying effect. It really gives teams more potential than you might think they would have. And just to give you an idea of the scale, so at Google, 10 years ago, they were saying that developers who were writing Java run this life cycle 6 times per day. And those writing in C++ ran it 10 times per day. So you can imagine and multiply that out by the number of developers at Google, and you see this pipeline really plays a key role. There's also this ragtag group of rebels. This is the Firefox release engineering team. Mozilla Firefox is a nonprofit organization that develops the Firefox web browser, for example. And I think that's really fascinating that this group of people is competing with folks at Google and Microsoft and Apple, right? And I want to zoom in on this particular guy who is named John O'Dwyn. He was the leader of this group. And he has a quote that I really like where he says that Mozilla's investment in their CI/CD pipeline is what enabled them to compete with the market giants in their area. So Google has the Chrome web browser, Apple has Safari, but Firefox is still able to establish a pretty significant market share on the web. So if you get the pipeline right, you can really do great things. But it's really easy to mess things up. Look at this stock image this time, right? So there are so many qualities that we want this pipeline to have, and getting them all right is tricky. So of course, we want it to be efficient. So efficient can mean 2 things. One is we want it to only use the minimum amount of resources that are required to check changes. The second is efficient in terms of what developers are expecting. So we want our feedback as fast as possible, right? But of course, on the other side of the coin, we don't just want it to be fast, we want it to do the right thing. So the pipeline should correctly scan changes. And that would mean making sound decisions about which tests to run and which ones to skip. And it would also mean reproducibility. So given the same change as input, we should get the same output. And finally, these pipelines aren't provided for free. There's some specifications involved that require developers to invest effort in keeping those pipelines performing the way that they expect. So we want those pipelines to also be maintainable, which means that we want them to be easy to extend, to add more checks, to add more components to the system, et cetera. And we want the pipeline to be debuggable. So when something goes wrong, we don't want it to give us something in the error log that's not so easy to fix, right? Okay, and the thing that makes these qualities so difficult to achieve is that they're often at odds with one another. Now, we can take the trivial example of speed versus soundness, right? So I can make my build go a lot faster. I can make this pipeline go a lot faster if I just randomly skip tests. But obviously, that's going to introduce some soundness problems because I'm going to allow broken changes through my pipeline, all right? And there are other trade-offs, such as, if I want my builds to be reproducible, that means we implement a lot more complex logic in our build, and that makes it harder to debug, right? So trying to maximize these trade-offs is one of the things that we, in my group, try to do. So we don't want to harm one of these properties too much, and we want to gain in the other properties. So the final thing I'll say to set the stage is that there are multiple stakeholders in this pipeline. There's the really clear example of the consumer, so that would be your developers, and they're shown given this very bright-looking face on our left-hand side. There's also the users. So as a former developer, I can't help but take a pot shot at users, right? But there's a third stakeholder, and that's the provider. So in the modern setting, it's quite common for this part of the pipeline to be provided by a third party. So some common examples are GitHub Actions, and some older examples, Travis CI, but these are third-party providers who provide like a specification format, often in YAML, that you basically describe your pipeline, and then they will perform the builds for you and report back. So we've done some research that helps both the provider and the consumer in the past. I'm going to focus today on the consumer side, but if you want to talk to me about the research we've done on providers, I'm happy to do it. So the consumer has two questions, well, two big concerns that I'm going to focus on today. So the first is, I've produced a change set, so does my change integrate safely, right? And the duration of the run affects how quickly this developer can get that answer, right? So we kick off the pipeline, and we're waiting, and we're waiting, and we're waiting, and we're waiting. The duration of this waiting period affects developers, slows down the velocity of your software organization. So one area in which research has focused, not just my group, but others, is speeding up this process, right? So the most naive or the highest level of granularity that we operate at is at the change set level. So does every change set need a full execution of the test suite, for example? Let's take a hypothetical change set that just updates the README file, right? Do we need to recompile the whole system and rerun the whole test suite to know that this is safe? I would argue probably not. But this whole general area tries to extrapolate risk of a change set to decide whether it's safe to skip the CI run or not. So we'll use this image of a crystal ball to illustrate that we're going to inject a classifier into this workflow. And the classifier is going to decide, is this change set highly likely to pass? If it's really, really likely to pass, then we don't need to burn our energy and resources checking it. We can just report to developers that this change is likely safe. If it's not likely to pass, then we'll run the whole pipeline. We won't just report that this change set is likely to fail, because developers would not react well if you just said, your change is going to fail and I don't know how, right? They want to see the error log to know how to debug. Okay. So how have people made this kind of classification decision in the past? past. So I'm going to kind of highlight some of the prior work and then some of our work. So there are folks who have looked at rules that we can derive from developer behavior. So modern CI platforms allow developers to write a little message in a commit that they think doesn't need to run through CI. So it will skip CI. So we've got a collection of history that describes the examples that developers have used to skip CI. And we can try and derive some rules from that so that we don't need to apply that label in the future. There are folks who have treated this as like a time series. And we can look at the prior build to try and infer whether the current build is going to pass. And this approach is called build fast. It'll come back in a little while. Some of the stuff that my group has added to this field is we do a lot of nitty-gritty stuff with dependency graphs. So the kind of decision-making tool that build tools use to skip or execute steps inside of a build phase. We work together with a large video game company called Ubisoft, and we implemented this approach in their setting using that dependency analytics approach, like deriving their graph and making decisions on the fly about whether we can skip or pass a test. We also mined examples of developers' specifications themselves. So we looked at the specifications to see if they've included little hacks to skip steps or skip phases. And we built a catalog that developers can use to apply those hacks in other settings, so to enable sharing of these acceleration approaches. So I'm going to switch now to the messy part. So this is a really nice idea, and I'm still very much invested in CI acceleration through this classification idea. But one of the problems that I see with it is that we accept this inherent cost-benefit trade-off between skipping things and safety, right? So I'm going to pick on this old paper from 2020. I can say it's old now because that's when I started here, right? So 2020, where they published some really impressive results. And they have a conservative setting of their approach that shows that they can be safely skipping 30% of the builds in a time period. So 30% of the builds, you don't even need to bother running. So that's a big savings if you imagine the millions or billions that large corporations are investing in running all of these builds, right? But at the cost of skipping some builds that would have failed. And they say that those are cases where they've delayed the failure feedback. And they say they do that for 15% of the failing builds. So they missed 15% by at least one. They skipped at least one build. Now, when I talk to my partners at Ubisoft and I say, hey, there's this really cool idea, we can save you lots of money by skipping builds, and we'll only delay feedback for this. It's when I talk about this second part that they say I would rather run all the builds and not delay any feedback, right? So accepting this cost-benefit trade-off is a challenge for industrial adoption. The second thing that I think is really interesting is as we were building the Raven build prototype with Ubisoft, we wanted to compare to a naive approach. So a naive approach that is just parroting the previous build result. So we would just look at the label of the previous build. If it failed, we would predict this one's going to fail. If it passed, we'll predict this one's going to pass. And I'm showing you here, each dot is a different project. And on the y-axis, I'm showing you the performance of the parrot approach. On the x-axis, I'm showing you the performance of a state-of-the-art approach. So we would hope to see things in this bottom corner here, right? What we're seeing is that there are actually some projects, and the gold diamond is the one that is at Ubisoft, where parrot is actually doing better than the state-of-the-art. So some naive approaches are actually still competitive. And just to show you I'm not biased, we even did it for Raven build. The results get a little bit better. The points are moved this way, but there's still a lot of room for improvement. The last thing I wanted to highlight here is about the acceleration and its risk at a finer granularity. So when we're skipping things inside of a build, we create the opportunity for bugs to slip through this pipeline. And one approach we use to study this is, let's imagine we have a commit. We're going to apply 2 sets of mutants. So mutations are just small changes to the code, right? And these are designed to mimic real bugs, right? So we'll inject the same set of mutants into 2 copies of the code base, and we'll apply the full build as a treatment to one. And if the tests catch the injected mutant, we say it's been killed, and let's say that the full build killed 4 out of the 6. If we move over to the accelerated build, you'll see that maybe a subset of those mutants are killed in that setting. And we call the ones that survive in the accelerated setting, but were killed in the full build setting, we call these gap mutants. And these are mistakes that are caused by our acceleration. What we found is that there are gap mutants in real projects when we apply this, and the reasons for the gaps range from problems with dependency tracking in the acceleration to flakiness in the pipeline, which leads to the second point I wanted to talk about, which is this non-determinism angle. So a lot of our research is assuming that this pipeline is deterministic. Given the same inputs, it's going to give us the same outputs. But there are a few reasons why that might not be the case. So one is environmental settings. So you might be relying on a third-party service, Amazon, and something happens and they go down. That can affect the outcome of your builds. You might have some order dependencies in your tests that are not observed in a parallel setting. You might also have problems with the code under test. So you might have a timeout setting, and the test happens to pass or fail if the timeout is triggered or not, right? So this is the second angle of this pipeline. We want to know reliably, does my change integrate safely? And for that, we're focused on the failing outcome or the passing outcome, okay? And it's important to recognize that this CI/CD pipeline plugs into a lot of different developer experience platforms. So again, we're going to use this handsome developer, and we're going to talk about when he uploads this change, he's going to ask a peer to review it, right? So somebody else on the team is going to check my change to see if there are problems, right? And during this process, it's very common for CI to run as well, so that your other human isn't looking at your code to find that you missed a semicolon that a compiler is going to find better than a human, right? So we would run the CI execution. And all of this would provide feedback to allow us to iterate on changes before they go out to our team or to our users. But what happens if this friend here, our CI platform, is unreliable? So he might say that a change has failed, and different organizations have different policies. That failure might prevent me from merging my change, right? So to combat this, platforms like Garrett, like a code review platform like Garrett, provides a feature called recheck. It's a big red button that developers can punch to say, I don't think this failure is my fault, please try again. Okay, so I would say recheck. It would run CI execution again, think about it for a while, realize it's Shane, so it must be safe, right? Okay, so what could go wrong with this recheck feature, right? So the first thing to notice is that developers have unfettered access to rechecks. So developers can punch this big red button as many times as they like. They're not paying anything for hitting the button, right? Second thing to notice is that there are no formal rules or societal norms that affect my behavior, right? So me punching recheck is not changing your opinion of me, right? So this might sound familiar to those of you who have taken economics classes as an opportunity for the tragedy of the commons, right? Where individuals are going to act in their own best interest. They're going to punch this button more than they should, right? So to check whether that's actually the case, we performed a case study of the OpenStack organization. OpenStack is a large private cloud infrastructure system that's implemented in open source. And they have tens of thousands of change lists and lots of revisions. And ICE is a former postdoc of mine. He led the study. And a couple of things that we found. So more than half of the change sets that fail have hit the recheck button at least once. And of those that hit the button, so we'll call a recheck chain something where it's failed and I've hit recheck one or many times, okay? So 58% of these chains never pass. So developers are hitting this button without really thinking about it, and they're spamming it in some cases. So again, we thought this would be a great opportunity to apply a classifier. And I think this classifier is cool because it has two uses on both sides, okay? So for a developer, they're spamming this recheck button. Our classifier might say, you know, this is really unlikely to change the outcome. Are you sure, right? And the other useful application is this bot might say this test has failed, and our model might say rechecking is really likely to make the tests pass, and it would say, you know, are you sure? And automatically rerun the tests without bothering the developers, right? And this project was led by Lisa, a former master's student of mine, and this figure kind of sums up what we were finding. So the two vertical lines are showing the thresholds. So if a change is 20% likely or less to have a recheck switch to passing, we would automatically skip that recheck, saving a bunch of time, but also costing some time for the rechecks that we skipped that would have passed, okay? And on the other end, if we're really likely to fail, then we would automatically rerun that recheck, saving a bunch of time. And this was, yeah, just published recently. So hot off the presses. So just to sum up what I've been talking about, I tried to focus on two aspects of CI/CD pipelines. So one is the duration, where we have this classifier being injected before we run the pipeline to skip builds. And we found a few challenges with adopting these approaches in practice. So there's the idea that there's an inherent trade-off between cost and benefit that a lot of industrial partners are not willing to accept. We found that there are some naive approaches that still compete with state-of-the-art. And we found that there are some challenges that are introduced by acceleration approaches that can allow bugs to slip through. So they're not fully safe yet. On the other side, we looked at the reliability of these pipelines. When they pass, they should continue to pass, and when they fail, they should continue to fail for the same changes. And we talked about how often these rechecks are happening. There seems to be a spamming effect, and the kind of classification approaches that we can apply to hopefully help in this problem. Yeah, that's me. I'm Shane, this guy over here. Happy to answer your questions now. Thanks.
When you get a test failure, what other information goes back to the developer other than this binary?
So you would get
Was
that.
it you who said you weren't allowed to use binary last night? Somebody said we weren't allowed to use the word binary.
It wasn't me, but You get a full report of the execution of the test. So it would tell you which assertion failed, et
So the
cetera.
max, as much as can possibly go back to them. Good.
Yeah, exactly. Yeah.
Yes. To what degree have you looked into the causes of the recheck? Because what I've seen is that you have somebody checks into the code that by the grace of God passes, but has a race condition in there. And that sails on, so the next person checks in something, uses the same thing. So their test is failing because a timeout problem was introduced by somebody else. So you're being mean to the second person.
Yes, yeah, exactly. So we're not sure at this moment who's to blame for the flakiness that caused the recheck to be run. I think that's an interesting direction that other folks have focused on. So the flaky test literature tries to figure out who's to blame for this. Instead, we're assuming that there's going to be non-determinism. This recheck solution seems to be prevalent. But yeah, I think figuring out at the time of introduction which change is introducing this non-determinism would be a super useful direction for the future.
Well, if you can identify that there's timeouts occurring in your test, big help.
Yeah, yeah.
Thanks for your time. So AWS has been doing work where they do this for proofs as well, like a formal proof that's checked by a bounded multi-checker in the end. Is that also an interesting direction to explore, where developers can maintain proofs because that gives them a higher guarantee for like the correctness of the code that you're looking at, and it stays proven over time with changes that come in.
Like, you mean formally proving properties of the CI/CD pipeline?
Yeah,
Is that what-
not necessarily the pipeline, but the code that you're looking at, but putting that the same way that you'd have unit tests that run in CI. You could have unit proofs that run in CI, except they work on, let's say, symbolic inputs rather than concrete values that you're testing. And so you can maintain the high guarantees that have been invested upfront, but through time.
So yeah, like introducing more formal or rigorous checks into CI. Yeah, that could be a really interesting direction. I wonder, I'm not super familiar with that line of work, but I wonder how they would go from like an existing investment in unit tests to the more rigorous checks. Like, I think that's going to be a challenge for large organizations, but absolutely, I think they complement each other, right? Yeah. Oh, sorry, one more?
Yeah.
She's the boss, she's the boss. One more? Okay, yeah.
You probably get this a lot, but if the developer in your picture is not human, unfortunately not human, do you have thoughts on how that affects the CI and optimizations? How it's affecting your tools?
So if the patches are automatically generated, so I think the same pipeline applies. I don't know so I don't know how an automatically generated patch would operate at the code review stage. I think that's an interesting question to ask. Like, would it respond to human feedback in the code review loop? But I think it's an important question, like how automation that I've seen being applied is usually helping developers to produce the change set. So there's still a human associated with it. But if we get to a world where it's AI bots everywhere, yeah, it's an interesting thought experiment, though. Yeah. Okay. Thanks, everybody.
start now?
Yep.
Okay, so, all right. So in science, like many problems in science, we face this question: what is the integral of a function? So in this particular example, I have a function f of x and t, and where we integrate, t goes from 0 to 1, and then we get the function s of x. Okay. While there are many different ways to solve this question, one idea is to think of this as an average over t. So we have given a function f of xt, we just simply take an average over t for specific x. The way you can do it, you can just simply randomly sample various t's, n t's, and then evaluate f of xt, and then just take an average, because it's an average, yeah? And this is an idea called Monte Carlo integration, which has interesting applications in realistic image synthesis. So in this case, we are actually simulating the light propagation within the virtual scene. And here's an example. Say you have this kind of a virtual scene where you have a light source on top, and then you are looking at it from the side. Then you wanted to know how much light is coming to the sensor after the light is bouncing around within the scene. And this could be formulated as the integration problem, which is also done by one of the UO alumni, Eric Veach. And because it's an integration problem, just like before, we can just simply take random sample or paths, and then take an average of each contribution to get the image. Okay? But then, since this is still an approximation, the key question is how accurate it is. Well, to do so, let's try to take a difference and then take an absolute value. So we take difference between the correct solution and the approximation by Monte Carlo. And after some derivation, we can say that this is proportional to 1 over square root of number of samples. Which means that if you render something, or if you generate an image with 32 samples, you get a little bit noisy image because it's a random estimate. But just by increasing the number of samples using the same technique, you get this image. Okay? So this approach in realistic image synthesis has a bunch of interesting properties that are very useful for computation. Like a quick preview, you can reduce the number of samples, you can get the noisy but reasonable image. It will converge just by increasing the number of samples. And it is very easy to parallelize because samples are all can be done in parallel. It consumes low memory, and also I will talk about this later, but the point-wise estimation is possible. Okay, so that was the integration problem, but what about this? Which is that we have given function f, and we want the derivatives of a solution to be equal to given function f. So this is called partial differential equations, and the goal is to find out function s of x and t such that this is satisfied. Okay? Again, while there are many different ways to solve it, one idea is to discretize the x. In this case, we have equal spacing in the space of x, where the spacing is delta x, and then we can approximate derivatives just by taking the differences and divided by the spacing, in this case, squared. Okay? To simplify the equation, let's say the spacing is just 1, and then we get this equation. And then we can just stack terms vertically for no reason, but then we can then interpret this as matrix vector modification, where you have corresponding coefficient multiplied to each term that's equal to the function given, f. And then because it's the same partial derivatives applied for every single location, we have a bunch of same numbers on the matrix, and vector of discretized solution and the vector of given function at discretized location. Okay, so this gives you a matrix equation that you can simply solve by inverting the matrix. So you get the solution, and this is what I call as discretize and solve for partial differential equations. And this particular approach also has been applied to Monte Carlo integration, not Monte Carlo integration, image synthesis in a different way, under the name called radiosity method. And it has an interesting history in computer graphics. So back in the 90s, where people have both Monte Carlo and the discretize and solve for image synthesis, people are just liking the discretize and solve. And there are some people even saying Monte Carlo is just too slow. It's never going to be practical back in the 90s, okay? But then, after some time, Monte Carlo started to dominate because computers getting faster, and then for reasons I will talk about later, it has a bunch of interesting properties that you can utilize. And then nowadays, essentially nobody uses discretize and solve, and everyone uses Monte Carlo method for realistic image synthesis. To the extent that certain graphics, video game graphics processing unit companies also has built-in hardware feature to accelerate this approach for image generation. Okay? And if I try to compare these properties that I mentioned, they are actually Monte Carlo is quite useful compared to discretize and solve. So say if you wanted to do preview, like I say in Monte Carlo, you can just take one sample, get the noisy estimate, and that gives you reasonable preview. But if you want to do discretize and solve, you basically need to solve everything at the resolution you want to solve. So that's gonna be not preview. And if you wanted to think about convergence in Monte Carlo, you can just increase the number of samples to get the right solution. But in discretize and solve, once you set the discretization resolution, it's gonna basically determine the accuracy you can get. And in terms of prioritization, Monte Carlo, you can just take number of samples in parallel. But for the discretize and solve, you need to solve matrix equation, where the matrix solver in highly parallel setting is not necessarily as easy as Monte Carlo. And also for the memory cost in Monte Carlo, you just need to take one sample and then keep the running average. But in the discretize and solve, you need to store entire discretized solution and potentially the matrix. And that is going to be a huge memory cost. And last but not least, in terms of the sort of a locality of computation in Monte Carlo, you can just estimate the solution at single given point. But in the discretize and solve, like I said, you need to discretize entire things and then solve for entire thing all at once. So it's globally coupled. But given this stage, right now in partial differential equations community, numerical solutions for partial differential equations are mostly done by this kind of a discretize and solve. So the natural question is, can we come up with Monte Carlo approach for partial differential equations such that we have all these good properties? Okay? And the answer is yes. And this student, Ryusuke Sugimoto, who is actually graduating, or maybe officially already graduated, was brave enough to join me when I talk about this idea to him. He actually, later year told me that I was crazy in a good sense, that I tried to think about this way, and he actually nailed it, and then turned this into his PhD work. So I wouldn't be able to talk everything about what he had done for 5 years of PhD study right now, but I will focus on one aspect, which is trying to solve the Navier-Stokes equation that is very complicated PDE, partial differential equations for fluid dynamics by the method of Monte Carlo. Okay? So here is the Navier-Stokes equations. Don't worry about the details. The only point I want you to get is that this is a complicated partial differential equations where mathematicians spend hundreds of years to try to solve this kind of equation. And for this talk, I will use a slightly different form of Navier-Stokes equations called vorticity form. Again, don't worry about what the vorticity is. The point is that this is complicated still. And I can simplify a little bit for the purpose of talk, but then it's still complicated. So how do we actually solve this using Monte Carlo, where the idea is to take random samples and then take an average? Well, if I look at the first equation, what we notice that this could actually be converted into integral. So using some vector calculus identity, we can convert this into what's called Biot-Savart integral. By the way, that is not what we found. As the name suggests, it's found by Biot-Savart. And then you can, since it's an integration, you see where I'm going? I can apply Monte Carlo. So you just need to sample random points and integrate or take the average. That gives you an estimation. But what about the second equation? Well, this is not still convertible to integration problem, but we can also take a look at another method that's being used in fluid dynamics community called method of characteristics. The idea is that trying to understand what's the meaning of this equation, and this is basically saying the omega, don't worry about what the omega is. Omega is constant, doesn't change over time along the magical curve called characteristic curve. And what this equation is saying is basically this equation. So say you start with the initial point x at times t equals 0. This stays the same over time along the magical curve c over time. Okay? And then this again leads to this kind of approximation, which I will tell you in a minute. So let's say you wanted to know what is omega at this location at particular time t. What that equation was saying is that if you try to sort of step back in time, a location that you get and omega evaluated at this location is roughly equal to omega at this particular location at time t. So this is connecting value back in time, delta t, and then value back in the current time. So using these two estimators, we can actually build a Monte Carlo solvers given the omega at time t equals 0, which is usually the case for Navier-Stokes equations. So again, what I want you to focus on is that these two estimators depend on each other in a particular way. So say you look at the U appears in both sides, and also the omega appears in both estimators. And the first one is essentially estimating U of xt given omega xt. The second one is estimating omega xt given U of xt minus delta t, one previous time, and also omega at xt minus delta t. So there's this kind of dependency. And this could be written as mutual recursion function given the base case omega xt x0. So if you're not sure, maybe you understand this our common language in the programming language. So you write basically two functions where it depends on each other in this particular way. And then you stop at the time that t equals 0 because that's given by user. Okay. And if I not convince you that it's actually is visual recursion, I will illustrate this equation and the program using this diagram. Say you wanted to estimate omega at a particular location in time t, then it depends on the omega in previous time step at different location, where the different location is specified this u, okay? But then u depends on, based on this equation, the other omegas at different locations at previous time as well. But then each of the omega is still unknown, but then you can also keep applying this process to go back in time a little bit and then try to figure out the location where you need to look up. And if you keep doing this, you reach at some point time t equals 0, which is given, and then the inference of omega at time t equals 0 is going to be propagated all the way back to the time you want to estimate. So maybe you're thinking, does it really work? It sounds like, no, it's reasonable, but then does it work? And then short answer is yes. So if I try to, so here I try to compare against ARM result and traditional discretizer solved in the center row and the bottom row. And then while they, of course, are a little different in the sense that they have different numerical errors, roughly speaking, they match. And then that's kind of a good sign. And if I try to sort of bump this up to 3D scene using Monte Carlo, because we don't need to discretize the space, we can handle this kind of fine scale details where you just have a bunch of triangles floating in space, and then that is very easy to do. If you wanted to do this by discretizer and solve, it's gonna be a nightmare. And you can also simulate smoke hitting a chain link fence, where the chain link fence is like really thin geometry. And if you want to solve this by discretizer and solve, you need to actually discretize the space to the extent that the chain link fence, or each of the geometry on the chain link fence is resolved by discretization. That's gonna be, again, a nightmare, yeah. And because it's based on Monte Carlo, you can apply a certain technique called variance reduction, which will accelerate Monte Carlo computation without increasing the computation time or increasing the number of samples. And here the point is that the reference simulation using many more samples matches with the one with variance reduction with lower number of samples, which is accurate, which is faster, of course. And then, of course, compared to one without variance reduction, which is the same computation time, using the fewer number of samples, it's going to be less accurate, but then we can increase the accuracy just by applying the techniques in Monte Carlo method. Okay, so while this is Navier-Stokes equations, what we realize is that we can also extend this idea to different kinds of partial differential equations. In image synthesis, I say you can formulate things as like an integration problem, but in other ways, you can also formulate this as a recursive integral equation like this one. Again, don't worry about the terms. I just wanted to focus on general shape of the function. And what we noticed that if you wanted to solve this Laplace equation, which is again Laplacian partial derivatives or second order partial derivatives is equal to 0, this PDE, or partial differential equation, can also be written as the integration problem, or recursive integral equation. So look at these two equations. Did you notice something? They actually take a similar form, or actually exactly the same mathematical form, which is called Fredholm integral equation of the second kind. And this mathematical identity helps us to apply Monte Carlo image synthesis technique on image synthesis to a solver for Laplace equations. That sounds like magic, but then we can actually do this. So just to remind you, here's how we do Monte Carlo image synthesis. We sample a bunch of random paths and then take an average of contribution. Exactly the same idea applies to Laplace equation. So here the Laplace equation, you have given the boundary value and you want to solve what is the value inside, that satisfies the Laplacian equals to 0. And then you basically just take a random path and then take an average. That's it. And then you get this kind of solution, which has a bunch of good properties still maintained for the purpose of solving partial differential equations. And then we discovered that this was also suggested by a different group of people back in, again, 90s or 80s, under the different name called Wacom boundary. And then we are the first to connect this back to Monte Carlo image synthesis because we basically have the same algorithm to solve different problems, integration problems, and partial differential equation problems. And just to show you what we can do with this algorithm, we can solve various different boundary values problems like solving for interior, solving for exterior, different kinds of boundary types like the Dirichlet, Neumann mix, and so. So this is pretty general algorithm that can potentially be used for different problems than what we actually see right now. So now that we have Monte Carlo for partial differential equations and integral equations, it sounds like we can just use Monte Carlo for everything. Well, not so fast, because right now Monte Carlo solver is quite slow. So on the top left, we have the traditional discretized solve approach, which takes this kind of under 1 second, and then like all the other Monte Carlo approach, even with the variance reduction technique that I talk about, is going to take maybe more than 100 times. Okay, and then of course it's a Monte Carlo. You can reduce the number of samples to accelerate the computation, but that is going to sometimes not work. If you reduce the number of samples too much, it's going to give you this kind of result. So you don't want to reduce the number of samples, but then you somehow want to still accelerate the computation. And there are a bunch of different ways you can do it. Like you can come up with better Monte Carlo techniques. You can try to have a hybrid between Monte Carlo and different techniques. Or you might notice that the choice of converting PDE to integral is actually not necessarily unique. So we might be able to come up with, here's a better integral for the purpose of Monte Carlo integration. So given this, it's fair to say that Monte Carlo is probably not for everything in the near future. And I would say maybe discretized solve will remain the main approach for now. But remember this slide that I showed you? Is this what you are thinking right now? Yeah, this guy back in, this person back in 90s say Monte Carlo was never going to be practical in image synthesis. This person was completely wrong today. So you might be actually wrong in thinking that Monte Carlo is not really the right approach today, because you could be wrong in 30 years. I say 30 years because it took, in image synthesis, 30 years for people to realize that Monte Carlo is actually the way to go. So just to summarize what I say, one can solve both integral and the differential equations using this same idea that generating random samples, evaluating function at random locations, and then just taking the average, which is Monte Carlo method. And this doesn't require any sort of a pre-discretization. You don't have matrix equations, and it's simple, general enough to apply to different ideas at different PDEs. And it's very easy to prioritize because you just need to sample various location. In my opinion, this is a future proof because once the computers get faster, it's going to be faster. So ask me again in 30 years whether I'm correct or not. I might be dead, but Okay, that's it I have today.
Why you're doing this with images, but with fluid dynamics, that example, presumably, it seems like you're doing the integration to refer backwards in time, whereas in fluid dynamics, I would think you would simulate forward in time, so you wouldn't need this backwards recursion, you just need time step forward.
Yeah, so it's just a computation that you're going back in time, that you're actually doing computation in forward as well. So like every single time, you are trying to go back in time to figure out what is the result at current time step, and then you still, change the time moving forward, compute the solution, and change the time moving forward and compute the solution.
Simulation, you know what was there for previous time step. In simulation, you know what was there in the previous time step, right? So you don't have to go back, you just have to go forward.
Yes, I think you have a good point. Like this is actually, in practice, we implemented this kind of approach where we don't necessarily go back in time all the way to t equals 0, but then try to cache what was computed before and then look up, instead of time t equals 0. There's one more question. Yeah.
Can't the same thing be said with regards to the Simpson rule approach that you had, basically of taking the non-probabilistic methods where you take the two endpoints and twice the middle, which is Simpson's rule, or used to be called that. It seems you can solve smaller subproblems far more quickly in that than solving the whole thing. Then you've got the one with a bunch of points you now can refine. You should be able to take advantage of the parallelism dramatically on that refinement.
So I guess the question is to think about
Well,
simple.
in some sense that, but in some sense it also strikes me that the best way is probably going to be some mix of the Monte, with some randomness.
Hmm? Yes.
And also some of the traditional deterministic
Yes,
rules.
you're absolutely right. Yeah, in rendering or image synthesis, we actually use sort of a semi-deterministic, semi-stochastic method called quasi-Monte Carlo, which is going to be faster than Monte Carlo, but then still retain all these properties. So we can apply, actually we did apply those techniques for the result you show.
Or maybe get rid of that square root of n thing lying around, which is a consequence of Monte Carlo.
Yes, so if you apply quasi-Monte Carlo, it's gonna be a little bit faster than 1 over square root of n. Yeah, okay? That's the point. Yeah.
Hello, exciting talk, and my question is very related to the previous one. So in discretized methods, there are some methods to increase precision by basically solving it on 2 grids and canceling first order and second order errors and so on. And I was wondering if Monte Carlo doesn't have the same chance, because if you solve the problem twice with small numbers of samples, this gives you information about the places where you need more samples. And I'm curious to hear what you'd like.
So are you talking about some sort of adaptive method?
Yes.
Yes, in Monte Carlo, there's an adaptive method called like adaptive importance sampling, adaptive control variate, where you can just take into account previous samples to generate a new sample or estimate a new with a new sample. So those kind of things is possible with Monte Carlo. It's actually much easier because you just need to do point-wise refinement as opposed to sort of spatial discretization, which might be.
Thank you.
Yeah.
go. All right, let's jump right in then. So, hi, I'm Craig, and thank you for including me in this event. It's a real pleasure to be able to share this work with you finally. I mean, after a couple of years of it being out in the world. So I'll talk about, well, aperiodic tilings and the Einstein problem. I'll spend a moderate amount of time just telling you about aperiodic tilings, which is a bit of an exotic topic, probably especially in CS compared to, say, a math department. And then I'll tell you the work that we did to solve the so-called Einstein problem. So first of all, a little bit about tilings. Tiling theory is, well, it's the study of the plane, a study kind of as a branch of geometry of shapes that fit together to cover the entire plane, R2 usually, with no gaps and no overlaps. And we can formalize all of that, obviously. And tiling theory, I mean, has a lot of beautiful applications and examples of its usage. I mean, obviously, M.C. Escher's art is a wonderful example of tiling theory. And he filled notebooks with tessellations made from animal forms and then would develop some of his favorites into more refined artworks like this lithograph, Reptiles, 1943. In other parts of the world, tilings are heavily used as architectural ornamentation. So this is from the Darbi Imam Mosque in Isfahan. And there's been a long-standing debate over exactly what's going on in this pattern. How, to what extent did the people who designed it have any understanding of quasi-periodicity, substitution tilings, and so on. And there are applications in manufacturing as well. This is a really great old diagram from 1944 from the mathematician Heinrich Heisch. Actually, it's Heinrich Heisch, his sister Ellie Heisch was also a professor, and Loaf. And they're showing how, if we slightly redesign the shape that maybe we're cutting out of metal or something, we can develop it into a shape that tiles the plane and reduce manufacturing waste considerably. We don't have to throw out as much metal. And in fact, for the last couple of years, I was consulting with a sportswear company, a manufacturer of sporting goods, doing exactly this. So it was really great to be able to apply this abstract topic, but in a way that actually I can say this many kilograms of material are not ending up in a landfill because we did that. Some standard kinds of questions you might ask in tiling theory, just to give you a flavor of where we're going. I mean, the most obvious one you might want to ask is, if I give you some shapes, can you show whether or not they tile the plane at all? Are there any tilings from some given set of shapes? Or maybe more precisely, given a set of shapes, can you characterize the world, the universe of tilings that they admit? And there are all these, there's lots of really amazing research in pure math on spaces of tilings. An abstract topological space where every point represents a distinct way to tile the plane with a set of shapes. Given a property that a tiling, you might want a tiling to have, does there exist a tiling with that property? And I'll give you an example of that flavor of problem, because it's one that's still open, and I've always loved it. Very simple one to state. Do there exist any tilings of the plane where every tile has fivefold symmetry? Not the whole tiling. There doesn't have to be global fivefold symmetry, just the individual shapes. Clearly true for one-fold, two-fold, three-fold, four-fold, and six-fold. And nobody knows if it's true for fivefold. And this problem is at least, let's say, 400 years old, because here's Johannes Kepler in 1619 experimenting with this idea and not quite succeeding, right? Because he was forced to use these overlapping decagons that he called monsters that obviously do not have fivefold symmetry, and all the other shapes do. And again, more precisely, you might want to ask a related question. If you have a property that you want a tiling to have, do there exist sets of shapes that tile in that way and only in that way? And as you'll see, that is a more precise question and leads to the notion of aperiodicity. So let me say a little bit about what aperiodicity is. In the Euclidean plane, we say a tiling is periodic, well, if it has a translational symmetry. If there's a way to pick it up, move it, and put it down again, and every tile lands exactly where some other tile was. And I can demonstrate this with dazzling visual effects. So if I slide this tiling along that long diagonal arrow, every tile lands exactly on top of some other tile, and the same thing would happen if I traveled along this arrow, and in fact, if I travel along any integer combination of those two arrows, the tiling lands on itself exactly. So that is a two-dimensional family of translational symmetries that partially define this tiling. So presumably aperiodicity just means that this doesn't happen. But actually, that's not quite it. There's a little more to it. Because in fact, it's really easy to construct tilings that are not periodic. Like just take this infinite grid of bricks and turn two of them sideways. I've just obliterated all translational symmetry from that tiling. And so that doesn't seem like a very strong property. That's kind of boring. And there are other ways to do it too. I can slide some bricks. I can just rotate them willy-nilly. And easily destroy translational symmetry. So if that were all aperiodicity was, presumably it wouldn't have been as big a deal. So let me explain what the difference is, right? It's the difference between that third category and fourth category, what I showed you earlier. A set of shapes is aperiodic. We're not talking about a tiling anymore. We're talking about shapes that may tile. A set of shapes is aperiodic if you can tile the plane with them but never periodically. Then we say they're aperiodic. So it's stronger than merely being non-periodic. It's sort of periodicity is impossible, cannot be accomplished. And I stole this great diagram from Jim Propp, who wrote an essay about this stuff. And he points out, like, given a set of shapes, you can ask two questions. Do they or don't they tile periodically? And do they or don't they tile non-periodically? Three of these categories are trivial. A shape that doesn't tile periodically, it doesn't tile non-periodically, that's just like a random thing, right? Like, I mean, and respect to Jim for using a cat. I mean, that's definitely the best shape to use here. A shape that tiles periodically but not non-periodically, a regular hexagon, right? The only tiling that you can make with this shape is the infinite regular tiling from hexagons. And as we saw, something like a 2x1 rectangle can easily tile both periodically and non-periodically. So really the only category that is mysterious here, that isn't trivially, has trivial examples, is aperiodicity. Sets of shapes that can not tile periodically and can tile non-periodically. Two different properties. So let's dive into the history. The very earliest stirrings of this question go back to the early 1960s. The logician and mathematician Wang at Harvard was working on models of computation and automated theorem proving to some degree. And in the middle of a paper about automated theorem proving, for reasons it's still not entirely clear to me why he kind of dropped this in, he had a section that said like a generalized game of dominoes. He said, let there be an arbitrary number of square plates, as he called them. So he wasn't really thinking geometrically. He wasn't thinking about tiles, but it was more of an abstract model. You have these square plates with labeled edges, numbers on the edges. And you're going to try to fill the plane with translated copies of these plates in such a way that neighboring plates, neighboring tiles, have to agree on their labels at that edge. So I can put a B next to an A. I can put a B to the right of an A, but I can't put a C to the right of an A because the 3 doesn't match with the 2. And these are now known as Wang tiles in honor of Wang. So one thing is immediately clear here, which is if you can tile periodically with a set of Wang tiles, if you can fill the plane with periodic symmetry with a set of Wang tiles, then there must exist a rectangle that kind of expresses that periodicity. A rectangle that he called like a torus or a cycle, where the labels along the right edge match the labels along the left, the labels on the top match the labels on the bottom, and of course all the labels agree in the interior as well. And the converse is true as well, right? If you can build one of these cyclic rectangles, then surely these tiles can fill the plane periodically because you just repeat this rectangle. So that part's easy. A set of Wang tiles admits a periodic tiling if and only if it has a cyclic rectangle. But now what else could happen? Well, at that point in his presentation, Wang conjectured that aperiodicity cannot exist. He said, well, there's a little bit of preamble here where he says, a conjecture that seems reasonable but has thus far resisted proof, says that basically a set of Wang tiles tiles the plane if and only if it has a cyclic rectangle. Now, if it has a cyclic rectangle, if it has one of these things, it certainly tiles the plane. And he's saying that if you can tile the plane, you can definitely find a cyclic rectangle, even if the tiling that you're talking about is not itself periodic. So he's saying that any such tiling is evidence of the existence of a cyclic rectangle. In other words, aperiodicity can't happen because as soon as you can tile the plane, you can tile periodically. That's what he's saying. Now, why was he interested in this question? Well, he was talking about what we now call the domino problem because his section, these are not domino. His Wang tiles are squares, they're not dominoes, so it's a little confusing, but because he called that section a generalized game of dominoes, it's still sometimes called the domino problem. So the domino problem is like the Wang tile narrow phrasing of the tiling problem. Given a set of Wang tiles, do they admit any tilings? And the really cool thing here, and the connection to theoretical computer science, in fact, is that if you conjecture that aperiodicity is impossible, then the domino problem is decidable computationally. There must exist a decision procedure, an algorithm that tells you if a set of Wang tiles fills the plane or not. Why? You just construct larger and larger rectangles, and eventually either you fail, in which case the shapes don't tile the plane, or you discover a cyclic rectangle, in which case they do. And the only way that could go wrong is if you can build larger and larger rectangles without ever discovering a cycle, and Wang is conjecturing that doesn't happen. A few years later, that conjecture was proven to be incorrect by Wang's PhD student, Robert Berger. So Berger proved that the domino problem is, in fact, undecidable. He showed that you can reduce a Turing machine to a set of Wang tiles. Now, in fact, that construction is really straightforward, actually. Like showing how to encode a Turing machine as a set of Wang tiles turns out to be pretty easy. You just have basically one tile for each possible symbol on your tape, together with whether or not that tile happens to contain the read-write head at that instant in time. It's more or less that. Now, that's an easy encoding as long as I'm allowed to define a special Wang tile that defines like the start of the computation, like this, the read-write head at position 0 at in state 0, and force you to place that tile. If I can say use that one, then the whole computation flows out from it. But if you don't let me have that luxury and you're allowed to just start with an empty canvas and place whatever tiles you want, that does not work. And you have to do a lot more work to force the computation to unfold and play out what the Turing machine does, starting from scratch. So Berger's construction is quite elaborate. He has this cool, like, nested structure of partial sections of the Turing machine tape that kind of talk to each other non-locally and eventually cause arbitrarily long sequences of computation to take place. And so the really cool part, the consequence of that is, given a Turing machine, that Turing machine runs forever, does not halt, if and only if these Wang tiles fill the entire plane. Because otherwise there'd be some limit to how big a register you could build, because eventually the Turing machine just wouldn't want to carry out that amount of computation. All right, so we don't go into the details of that, but Berger's construction sort of relies on a skeleton set, he called it, of 20,000 tiles, into which he stitches the tiles that make up the Turing machine, but the skeleton structure gives you this hierarchical construction. Now, here's the really cool part about this, right? If aperiodicity were impossible, then the domino problem would be decidable. So if you've proven that the domino problem is undecidable, aperiodicity must happen. There has to be an aperiodic tile set, the contrapositive of that statement. And it turns out, sure enough, that Berger's skeleton set, sort of with a null computation, you just make the computation trivial, you get a set of 20,000 tiles that tiles the plane aperiodically. So that's the very first aperiodic tile set. And there was progress, even in Berger's PhD thesis, he said, actually, you can do it with like 100 tiles. You don't need 20,000 tiles, that's ridiculous. And of course, as soon as you say that, like, oh, it was 20,000, now it's 100. Actually, Berger said in his thesis, I've made no attempt to verify that this is the smallest set, right? So, of course, everyone's like, okay, it is on. Let's see what we can do. And there was a sequence of smaller and smaller sets of aperiodic Wang tiles throughout the 1960s and 70s, getting down eventually to around 24 in 1975. Even Knuth got in on this game. He proposed a famous set of 92 tiles, et cetera, et cetera. And this became an interesting research topic all on its own. In 2021, Jendal and Rao finally settled this question, proving that, in fact, 11 is absolutely minimal. And they did that by exhaustively computing the tiling status of all sets of size 10, and proving that none of them were aperiodic, and exhibiting a set of size 11 and proving that it was aperiodic. So, but that, that's pretty recent, right, for settling this complicated problem. Now, so far, none of this, does this look like, it doesn't look much like tiling theory. Like this looks much more like computation or combinatorics. It doesn't look, they're not thinking geometrically when they're working on these problems. And so a real breakthrough in my mind came in 1971 when Robinson proposed this set of tiles that really do look like tiles, that they fit together by virtue of their shapes and not abstract symbolic labels, which can be encoded geometrically, but that's not the problem they were actively trying to solve. Whereas Robinson said, you know what, let's just pretend, let's just say these are just geometry. As long as you can fit these together with no gaps and no overlaps, and you should feel free to rotate and reflect them however you want, Wang tiles were translation only, then I can still guarantee that this set only tiles non-periodically. And the way this is usually done, I'm just going to say a tiny bit about it. First of all, we sort of reimagine the geometric markings back as symbolic labels because these are sort of easier to understand in terms of visual intuition, but it's very easy to say, oh, and we're going to introduce rules. We'll say when I put tiles together, if there's red stuff on an edge, it has to match red stuff on the other edge, and when two tiles are next to each other, their arrows have to point in the same direction. They can't butt heads or point away from each other. And this is, tiling with those rules, with these shapes, is exactly equivalent to tiling with just those shapes. And what's cool is Robinson showed that any tiling by those shapes inevitably ends up looking something like this. You get this infinite nested pattern of squares of every size. And what's the great thing about this is basically an immediate proof that any tiling by these shapes must be non-periodic. Because if you propose a translational symmetry with some vector, I'll just show you a square that is much bigger than your vector. And no translation of the tiling can possibly map one of those giant squares onto another copy of itself. So that your vector cannot be a translational symmetry. And therefore, as long as all the tilings by these shapes have these nested squares, no such tiling can be periodic. So it's an aperiodic set of size 6, down from 20,000. How low can you go? Well, just a couple of years later, of course, the biggest breakthrough came from Roger Penrose, who found two sets, both aperiodic, so these are two different sets of tiles, both of size 2. Initially a set of size 5, and then from those he derived these two sets. One is usually called the kite and dart, one is usually called ROMs, or thick and thin ROMs, or what have you. These shapes have to be annotated with extra little bumps and dents to prevent them from fitting together in ways that would be periodic, but with these markings, you only get non-periodic tilings. The kite and dart, just to focus on that for a second, the way you tile the plane with kite and dart is to invent what are called substitution rules. This is almost like a context-free grammar sort of thing, a way to rewrite a little patch of shapes with a patch of more shapes. And you just iterate that process, generating bigger and bigger patches of shapes. And then, through a very non-trivial mathematical fact, you are allowed to take the limit of that process and get an infinite tiling of the plane by these shapes. But this is a very simple, elegant idea. So you could start with a kite, use that rule to get 2 kites and 2 darts, and then use the rules on all 4 of those shapes to get more shapes, and so on and so on. And there's a little bit of slop where these shapes hang over the boundaries of the original tiles, but you can work out that when that happens, the tiles that are tiles will overlap but in perfect agreement, so there's no inconsistency there. And for example, if you iterate the rules for the kite and dart, and then, well, suppress those bumps and nicks because they're a little bit ugly, you get these beautiful tilings of the plane with all sorts of magical properties. So, to summarize, we started with 20,000 shapes in 1964, and around 1974, we were down to 2 shapes. Excellent. I feel as if there is one more step to go, and in fact, this became arguably the major open problem in tiling theory, the question of whether there exists an aperiodic monotile, a shape that is forced to tile non-periodically all on its own, just one shape. This is sometimes also called the Einstein problem, and that is essentially a dumb joke by a mathematician named Danzer from the 1980s. It has nothing whatsoever to do with Albert Einstein except as a pun, right? That's why we say lowercase e, no disrespect to Albert. It's just from the German Einstein, one stone, because you're tiling with copies of one shape. It's like the tiling theory dad joke. It's great. Okay, so that's the question that remained after Penrose's discovery. And the first time I can find this question in print, I'd love to find earlier instances of it, because I don't think this is the first time someone articulated the question. But in Mathematical Games, Martin Gardner in 1975 wrote, "Is there a single shape that tiles only non-periodically?" And you can see, like, this is as part of a larger discussion. We know it can't be convex from R.B. Kirshner's results, blah, blah, blah. These results were later falsified and then finally settled by another proof by Michael Rao, but that's another story. Anyway, that's okay. Kirshner took it all in good humor, so we don't have to worry about it. So since that time, arguably there have been a few close calls, a few shapes that kind of made progress towards being, earning the title of an aperiodic monotile. But as my co-author Joseph Myers wrote in our paper, I thought it was really clever. He said, but all of these push the boundary of the notions of tiling, or aperiodic. They all play a trick. They're not quite what we want, even if they are really impressive achievements on their own. We're not going to go into details on these, but as recently as 2011, there was a paper that's like, here's an aperiodic monotile, actually even more recently, but asterisk, right? There's always terms and conditions. And we still, people were searching for the unconditional thing that, kind of had this, behaved like this. It was just a shape, and all you had to do was fit copies of that shape together. All right. So that takes us up to 2022, and essentially, from my perspective at the time, a random guy on the internet. Thank you, random guy on the internet. So I knew Dave Smith a little bit. He was an acquaintance from email and mailing lists that we both belonged to for people interested in tiling theory. And he's not a mathematician. It says retired print technician, so he used to operate large format printers and do paste up, before digital typesetting and so on. And was retired. And he just likes to play with shapes, sometimes by drawing them on a computer, sometimes cutting them out with a digital craft cutter and just working with his hands. I had seen, based on stuff that he had posted to the mailing list in the past, I knew that he was no slouch. I knew that he had excellent visual intuition. So when he emailed me, I paid attention. That's the point I want to make. I'm like, yeah, this guy definitely knows what he's doing, and I should stop and examine what he's sending me. So in November of 2022, he sent me this shape. You may have seen it. He sent me that shape. You can see that this shape, which we now call the hat, is very simple. It's the union of 8 kites from this underlying simple grid, which has different names. You can call it like the kite grid. You can call it the Catalan tiling 3464. It doesn't matter. And you can see that he had already done a few preliminary experiments where he, as he said to me, I was able to build out pretty far from a central shape without getting stuck. although it took a lot of work, this is very promising, and doing the same thing with paper. So he contacted me asking if I could help him understand how this shape tiled the plane, knowing that I had software that could probably automate at least this step, right? Allow us to make much bigger patches of tiles to try to understand what was going on. So now, with my software, the interesting part that I want to say here is, normally, if you just pick a shape and pass it into my software and say, build a big patch of these, one of two things happens. Either it obviously doesn't tile the plane, or it obviously tiles the plane periodically. This is the norm. And I mean, obvious is not exactly obvious, so let me explain a little bit. What my software is saying with this output is it says, I was able to surround the shape once, and I was able to surround that a second time. So the light gray layer and then the dark gray layer, and then no matter what I do, I get stuck. I can't surround a third time. And you'll take my word for it that what my software is checking that exhaustively. It's saying there is no conceivable way to add a third layer of tiles, so clearly this shape does not tile the plane. And then this, like, the tiles are colored by orientation, which is a little bit of a visual cue. I've done this long enough that as soon as I see this, I'm like, yep, obviously periodic. But if that's not too convincing, then coloring it in can help and bring out the repetition, right? This is clearly copies of this like gray flower with a few pink and white things in different orientations, repeating periodically, and a little bit of extra slop that the program was able to generate along the periphery where there are fewer constraints. So it just kind of, it says, yeah, I'll fill in a little bit more there. Now, when we plug Dave's shape into my program, we got this, which is absolutely mind-blowing. My God, no, from the perspective of having worked on this for a few years, as soon as I saw this, hair on the back of the neck standing up, like, this is a huge moment. Because the fact that it's able to get out this far at all is enormously strong evidence that this shape actually tiles the plane. Like, why would you get out this far and then get stuck? So this is strong, or looked at another way, there's an open question about if a shape doesn't tile the plane, how far can you build outward from a central copy? And the largest answer we know is 6. And this is obviously much more than 6. So even if this shape happens not to tile the plane, it's already like it more than doubles the existing record. Fine. So let's take that as evidence that it does tile the plane, but it does not have any obvious repetition. It doesn't look totally chaotic, but there's some structure here that needs to be pulled out. And that's what Dave and I set about doing. We started exchanging emails very frequently, sort of saying, what can you see here? Optimistically, you make the assumption there is structure. There is structure that can be understood from this arrangement of hats. How do you find it? Well, I mean, it's basically an exercise in coloring, right? You try to pull out features of interest. The first thing we did was we said, well, there's an interesting mixture of, call them regular hats and reflected hats, or left-handed hats and right-handed hats if you want. And you can see, like, here's a regular hat with the kind of flat side on the left, and where did I see one? There's a reflected hat with the pointy bit on the left. Fine. So I will color all the reflected hats in a contrasting color, and I get this. And this is also mind-blowing, right? There's no way that my software that just says, just fill the space, I don't care how, would sort of randomly choose today to space out these reflected hats in this very regular pattern. So this is eerie, right? It's uncanny. And then we noticed that each of these reflected hats is surrounded by a small cluster of neighbors in the same way. So let's color those in. And like now, there's just a lot of, there's something going on here. There's all kinds of structure that we will hypothesize the software that generated this patch was forced to use in order to make this shape tile this much. And eventually, that allowed us to start to reverse engineer rules that account for the structure of what we were seeing. And what we ended up with looks a little bit like this. We defined a kind of intermediate abstract tiling that allowed us to kind of negotiate the problem of tiling by individual hats, but at a higher level. So we define these 4 groupings of hats, 4 hats, 1, 2, and 2. And these are identical, but don't worry about that. They're going to play slightly different roles in the tiling. They're kind of, you can think of them as like having slightly different semantic relationships to the rest of their neighbors and so on. And we take these clusters and give them simplified outlines where each outline has some, well, these are actually magic triangles, 30, 60, 90 triangles. It has some sticking out triangles and some indented triangles that force those simplified outlines to fit together only in certain ways. If you treat them as being something like the numeric labels on Wang tiles, right? It says you can only attach one of these abstracted shapes to another one if they agree in terms of the bits of hats that are sticking out or recessed. And we call these meta tiles, these 4 shapes. And the nice thing about these meta tiles is if you can prove that the meta tiles tile the plane in a way that is consistent with these bumps and nicks, then of course the hats have to as well, because you construct the tiling by meta tiles and then just transcribe the hats in the final step. And so if for whatever reason these 4 shapes are easier to work with than the hat itself, then that's a win, right? It helps us make our proof. And sure enough, nice thing about this is we were able to come up with substitution rules, like the Penrose tiles, for the meta tiles. So these 4 tiles can each be replaced by a little cluster of the 4 meta tiles. And we can ignore the dotted parts for now. But they either you take them into account, in which case, as with Penrose tiles, the dotted tiles from neighboring clusters will overlap and match perfectly, so it's okay. Or in fact, if you just leave them out, everything fits together perfectly like puzzle pieces. So that's great. And you take these substitution rules are a little bit more complicated than the ones that existed for previous aperiodic tile sets. Fine, we're going to gloss over that for now. The point is, if you iterate the substitution rules, you get larger and larger patches of meta tiles and thence of hats themselves. And once again, you invoke this very powerful topological compactness theorem from tiling theory called the extension theorem that gives you permission to iterate this an infinite number of times and obtain an infinite tiling as a result. Not obvious at all, but, well, I mean, compactness theorems in math are often like very indirect and not obvious. So it's just, join the club. And so we're done, right? Like that's it. We proved that tilings by hats are non-periodic. Not so fast. I invoke the specter of this diagram one more time. Just because I was able to contrive a non-periodic tiling from this shape, it does not guarantee that every tiling by this shape is non-periodic. So I still have to do the heavy lifting of ruling out periodicity. Saying that this shape tiles, and I should say, like, how do I even know this is non-periodic? Like, maybe I just iterate to infinity and I get a really boring tiling that's periodic. Well, it turns out to be not too hard to prove that tilings generated by iterating these substitution rules must be non-periodic. There's this very nice, when you have a substitution system, there's this very nice matrix you set up, and if the eigenvalues of that matrix are irrational, boom, non-periodic. And because it implies that, for example, the proportion of tiles that are reflected is an irrational number. And as soon as that proportion is irrational, the tiling can't be periodic, because in any periodic tiling, there has to be rational relationships between every kind of tile and every other, because the relationships are defined by what happens in one rectangle. Yeah. And it turns out, someone was asking me about this yesterday, the ratio of reflected hats to unreflected hats is exactly 1 in the 4th power of the golden ratio. Golden ratio, get out of here! It always tries to creep into everything. But yeah, here it is again in this tiling. Anyway, so knowing that the tiling's non-periodic means that we're definitely in the right-hand column, but we have to prove that we're not in the bottom row of this table. And at this point, frankly, it was time to call in some more muscle, right? I mean, my intuition definitely got us this far, trying to reverse engineer these rules, which was tons of fun. But most of the papers I write are not theorem proof, theorem proof, theorem proof, and we needed help from mathematicians who do write papers that way. So we reached out to two mathematicians, Chaim Goodman Strauss, who was at the University of Arkansas, is now the outreach mathematician at the National Museum of Mathematics in New York City. Wow. And Joseph Myers, who was a PhD in combinatorics and graph theory, is now a software developer, but in the software development world is maybe most well known as, he used to be the maintainer of GCC, the project lead for GCC and glibc, so he's a good coder. He's all right. All right, his code, he writes impressively performant C code. So we have to rule out periodicity. In other words, we have to solve the problem given a tiling by hats. Like, I look away and you prepare an arbitrary tiling by hats using whatever rules you want. How do I prove that that cannot be periodic? And the idea is going to be that we prove that first, even though I was not involved in the preparation of your tiling, I can prove that the tiles have to group unambiguously, with like no room for error, into the meta tiles that I've defined. And then furthermore, that the meta tiles can be like unwound into larger copies of themselves according to my substitution rules. And we'll see, that turns out to be enough to prove non-periodicity. It's essentially a giant case-based analysis. You look at all possible ways tiles can fit together or not and show that no matter what happens, you get my rules. You see the imprint of meta tiles and their substitution rules in any tiling no matter what. It's certainly a messier case-based analysis than Penrose tiles. This is Ed Robinson tiles as well. This makes sense, right? I mean, those tile sets were hand-constructed to have the properties that the mathematicians who made them wanted. Whereas ours, well, we just kind of found it lying on the floor and said, well, what's this? And you have to work with what you've got and hope that it has rules that can be understood. So it's messier, but on the other hand, I'm a computer scientist, Joseph is as well. We were able to streamline the proof considerably with computer assistance, right? We were able to write code that ground through the case-based analysis for us. So just to give you a picture, I always wanted to make this picture. This was an opportunity. Just to give you an example, you can sort of enumerate exhaustively every possible small cluster of tiles that may occur in any tiling by hats. You sort of, just every possible way you can have a hat with a layer and another layer around it and the potential for another layer around that. There's only 188 of them. It's an easy piece of code to write. So we call these the surroundable two patches. And in any tiling by hats, in any tiling by this shape, every individual hat has to lie at the center of one of these 188 things. And so if you want to understand the tiling as a whole, and you can do an analysis tile by tile, you can sort of stitch all the answers together and get the information you need. And that's what we do. We sort of say, okay, for this particular surroundable two patch, here are some rules that we define in the paper. Details are in the paper. Love that. Here are some rules that we define that allow you to recover a little fragment of the division into meta tiles. And if you do this everywhere, then these little fragments all assemble together correctly without any inconsistencies, and you can recover the meta tiles. And so, with rules like that, given sort of an undifferentiated mass of hats that, for whose construction is unknown to me, I can nevertheless perform this kind of analysis and discover the division into meta tiles that these hats are forced to have. They are orderly enough that these meta tiles always exist and are consistent with each other. And then I can turn the crank one more step and say, oh, and by the way, with additional rules, these meta tiles must unambiguously reassemble into larger clusters that are associated with meta tiles at the next level up in this hierarchy, the ones that, if you were to apply the substitution rules, would get you back from pink to black. And the great thing about this is that having gone this step from black to pink, this is now recursive. If I can do it once, and if I can show, and by the way, the pink stuff has the same combinatorial structure as the black stuff, I can iterate it as many times as I want. I can go, okay, well, now the pink stuff has to assemble into even larger yellow things, which assemble into even larger things, and so on ad infinitum. And now, the amazing thing about this is this infinite hierarchy of larger and larger metatiles behaves exactly like this infinite hierarchy of nested squares in the Robinson tiling. It is enough information for us to guarantee that the tiling by metatiles, the black stuff, and therefore the underlying tiling by hats must be non-periodic, right? So now we have both sides of the proof that we need. By iterating the substitutions in the first place, you're able to produce non-periodic tilings. So they exist. And by backing out from any tiling up through this infinite hierarchy, you know that any tiling from these shapes must be non-periodic. Therefore, the hat is an aperiodic monotile. So that was the first proof in our paper. And frankly, I think we said this in the paper or maybe somewhere else. The proof is basically unenlightening. It's like there is no step in that proof that could not have been done 50 years ago if only we had known what shape to try it on, right? It's very elementary techniques, which is fine. Good thing too. But the cool thing is it was a breakthrough. It finally resolved this open Einstein problem. We were able to get down from Penrose's 2 shapes down to 1. But there's a little bit more to say. This is like the Steve Jobs portion of the talk. Well, I actually have one more thing I want to show you. I have a few more things I want to show you, actually. Rewind the clock. Dave sent me the hat in November of 2022. About 2 weeks later, he said something. I was sorry to bother you. I found another shape. I hope that's not inconvenient. Right, he actually found a second shape that appeared to be doing similar things. And I said, oh my God, can I please put this on the back burner for now? We won't think about it. Let's work on the hat first. After we had our proof of the aperiodicity of the hat, and I guess, by the way, right, as I said, we reached out to Chaim Goodman-Strauss and Joseph Myers in early January saying, can you help us finish this proof? Basically, Joseph finished the proof. Chaim was busy moving to New York. Joseph finished the proof in 8 days. It's like, this is not how math research is supposed to get done. Not that I object. I'm not going to count on it every time. Be nice. So Joseph really nailed that quickly with the assistance of computation. Anyway, so I mention this because after he had resolved that pesky hat tile, he said, well, let me now take a look at this thing. And he applied the computations he had developed for the hat to this shape, which we call the turtle, and discovered that like all the numbers, all the combinatorics, all the properties that he was computing, he was always getting the same answer as he was for the hat. So that's too good to be a coincidence. The turtle must somehow be a hat in disguise in some way, right? And so the question is how? How are they related? Well, it turns out Joseph realized at that point that the turtle and the hat must be merely 2 points along an infinite continuum of shapes, all of which tile the same way. So in fact, we didn't, you're welcome, we didn't just find an aperiodic monotile, we found uncountably many aperiodic monotiles. Not in a very interesting way, but I'll take it. If I earn 1 penny for each one. No, okay. So we have this continuum that we refer to as tile AB. It's not too hard to see that this works because it turns out the edges in the hat come in exactly 2 lengths, which we can call 1 and square root of 3, and the edges of each length come in parallel pairs. So I can take like all the length 1 edges and just stretch them out, and everything like slides away from everything else. Do the same thing with the root 3 edges, and I get a new shape, which is closely related and magically just tiles exactly the same way. And this whole continuum is aperiodic monotiles, with the exception of this degenerate one where one of the edges goes to 0, you get chevrons. This one, the other set of edges goes to 0, you get comets. And this thing in the middle, that's equilateral and just happens to allow a little bit of extra adjacencies that the hat does not. So if you leave those out, Joseph developed, and I say ingenious because it was Joseph's idea, he then turned this continuum into a second proof of the aperiodicity of the hat, which relies on combinatorics and number theory and symmetry. It's really quite amazing. It's sort of like start with hats, drive the continuum to that limit, and then show that those two tilings, the chevron tiling and the comet tiling, have to have this number theoretic relationship with each other that they can't have if you hypothesize that the hat's tiled periodically. Therefore, the hats have to be aperiodic. That's as much as I'm going to say about that. So this paper came out, we put it on archive March 20th, something like that, in 2023. The reaction was generally positive. There were still a few skeptics. Some people responded saying, okay, this is cool, I like it, but I think you're using two shapes. Are left and right-handed hats the same shape? Like, if you have to use left and right-handed copies of a shape, maybe those are different. Are they the same shape? Yeah, look, if you ask me as a mathematician, the answer is absolutely yes. The first person to say a shape and its reflection are congruent was Euclid. I trust him most of the time. But even if you look at references on tiling theory, left and right-handed copies of a shape are the same. So I think that's probably going to fly. Nevertheless, as a mathematician, as a computer scientist, you say, okay, but this raises a good question, which is, what if you wanted to tile aperiodically but not use reflections? That is absolutely a valid question, and arguably the most significant open question that emerges as a consequence of our paper, right? We say, we believe that this is an aperiodic monotile, but wouldn't it be nice to answer this as well? We didn't put that in the paper because we didn't even consider this particular response to the work, but it's a good point. So we along with the rest of the community, settled in, hoping that somebody would come up with a solution to this subproblem. And Dave did so 6 days later. So I said he had good intuition, right? Dave kept fiddling around, and in particular, he got obsessed with this tile 1-1 shape, the equilateral member of Joseph's continuum. Now, in our first paper, we said, yeah, we're going to discard this one because it tiles trivially, periodically, if you mix left and right-handed copies of this shape, right? Just these are right side up, these are upside down, and so on. And Dave just wondered, well, wait a minute, what if I didn't allow myself to mix left and right-handed copies of the shape? I don't know why he was motivated to consider that, but he considered it. He said, what if I only use one color of tiles in this diagram? And he discovered, sure enough, it was behaving strangely. Not the same flavor of strange as hats and turtles. This is not the same tiling. So, we had to come out of retirement 6 days later, the group of the four of us. We say, okay, we got a new problem, let's work on it. And basically spun up exactly the same machinery a second time. Let's computationally generate large patches of this shape and try to understand the structure. And once again, there seems to be this sparse arrangement of special copies of the shape. These are not reflected, so they're not left versus right-handed, but these are rotated by odd multiples of 30 degrees, and all the other ones are rotated by even multiples of 30 degrees. So think of them as odd and even tiles, and you get this sparse distribution. And then I figured out that you can basically cluster the tiles into only two distinct clusters in any infinite tiling by this shape, at least based on the evidence of these finite patches. And you get this sparse arrangement of secondary tiles, and everything else is these orange things. And of course, I've got this fine-grained sparse distribution of something, and I've got this coarse-grained distribution of clusters of somethings. That kind of suggests a substitution rule waiting to be found, right? Somehow each of these is going to expand out to be one of these, or something like that. And eventually we did identify the substitution rules, or a set of substitution rules that drives the creation of tilings by this shape, where you define basically two distinct tile shapes. One is, that thing up there, tile 1-1, and this is a union of two copies of tile 1-1, which, to all of us at least, looks uncannily like a Buddha in seated meditation, and so which we eventually called the mystic. It's great. It does. And what's really cool about these substitution rules that's very unusual is every tile in the substituted patch is reflected, but they all reflect together in sync. So you never need a mix of reflected and unreflected tiles, but to make the combinatorics work out, you need to, like every generation, you need to reflect everything, and then reflect again, and then reflect again. And you can iterate those rules and get larger and larger patches of these tiles. And of course, you can think of this as being two distinct tiles, a single specter and a mystic, but of course, the mystic is just two specters, so when you're done, you split them apart and you have a tiling by that one shape. You again need to do a lot more work to prove to yourself that any tiling by these shapes must be non-periodic. Again, that does not follow directly from this sequence of iterated substitutions. But we furnish such a proof in a second paper, and it's basically the same style as the proof in the first paper. You show that in any tiling by this shape, there is a unique, unambiguous way to cluster tiles together into larger and larger groupings, and because you have this hierarchy on top of the base tiling, that hierarchy guarantees non-periodicity, like those nested squares in the Robinson tiling. Now, there is one asterisk here. It's like, as I said, we still have to prove that every tiling by this shape is non-periodic, which of course is false. Because this one is not. This one is periodic. So wait a minute, I'm lying, right? I claim that every tiling by this shape is non-periodic, but then we already knew that wasn't true. But the cool part is, it's very, very easy to modify this shape and produce infinite families of new shapes that only tile in this way and not any other way, right? Because this shape is never able to meet its reflection. If you reflect, the curves kind of go all the wrong way and nothing fits together anymore. And so these kinds of modifications force all the tiles in any tiling by this shape to have the same handedness, and therefore tile non-periodically. So this became, called specters, this is an aperiodic monotile that never uses reflections. And so, that really silenced the haters online. Yes, gotcha. All right, cool. Which was really the goal. No, okay. Why do you think I do this? Okay, and so yeah, you can see that you start with a tiling by these polygons, but from that you can derive a tiling by any number of different curvy shapes that can only behave this way. It's very cool. All right, so we put the second paper online, and it joined the first one, and lots of people became really excited about this work. And so I want to say a little bit about what happened after by people other than me, just for fun. I should say, why does this work? I mean, there are all kinds of things that are unsolved here, that are unaccounted for. I mean, fundamentally, right? I should go back, right? Andrew Wiles, who proved Fermat's last theorem, famously described the process of doing math as like stumbling around in a dark room, and you feel the outlines of the furniture, and eventually you find the light switch, and suddenly everything in this room is clear, and you see the door to the next room, and you continue on your journey. Well, finding the hat, is not the light switch. Finding the hat feels like bumping into a coffee table, right? It's like one little data point that does not really explain what aperiodicity is. And so there's still a lot more to be understood. Why did it turn up in a polykite and not like a polyomino, polyhex, poly anything else? No idea. Why didn't we look there 30 years ago? No idea. Why was this shape hiding in the continuum containing the hat and the turtle? That to me is the biggest mystery of all, because it doesn't even tile in the same way. It's a totally different thing. Is Dave Smith like the modern day Ramanujan who received the whispered secrets of the gods and had this tremendous insight, or is there some deeper connection that's yet to be found? I'm not sure. So people have done some pretty cool follow-up work trying to find interesting practical applications for our shapes. You can sort of understand the impulse for people who do engineering, material science. They're like, ooh, new shape. I wonder what it does, right? And they subject it to all manner of tortures, which is great. Like, let's pull them apart. Let's push them together. Let's twist them. And so there's been a lot of fun projects involving metamaterials and electrical engineering and wiring diagrams and quantum physics trying to understand, does this shape behave in some interesting new way that we haven't seen before? And there's some results that are like, yeah, this thing's cool if you squish it. It squishes in a particularly nice way, I guess. I'm not really following the research closely. I just kind of took a tour through some of the work that has cited us. Here's a couple of other papers in slightly different fields. These are building sensor arrays, and they claim that the kind of irregular distribution of points in these hats gives you a sensor array with better bandwidth. Don't ask me to explain how exactly that might work. It's not really my field. And this is trying to use the same kind of distribution of sensors, but in the context of seismology, I guess. So they're saying we should put a network of sensors here arranged according to specters on this mountain, and we'll be able to detect wider bandwidth of tremors. Here's a nice engineering application. So this was sent to me just a couple of weeks ago, earlier this month. This is an engineer who makes antennas, who built his own custom, these are called lapping plates. If you want to very finely polish a disc of metal, you can press another disc of metal onto it with an abrasive material in between, and you polish. And that's called lapping. And he hypothesizes that a lapping plate where the network of channels for the abrasive is hats will outperform a lapping plate with like a square grid on it or something, because it suppresses more frequencies that might leave artifacts on the lapped surface. And I hope he's right. I'm not fully I feel like maybe a lot of these claims are a little bit overblown, right? It's not clear to me that the magical mathematical properties of the hat will translate into actual magical physical properties of physical hats. But the jury's out, and I'm happy to see people playing with this. My favorite one of all is probably this one. In 2023, I received an email from someone named, I'm a University of Waterloo math student, so that's great. I'm on a co-op term at a company, great. The Spectre has shown promise for one of their current projects, hypersonic transducers for use on Mars. Please, 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 please. Go to Mars, hats on Mars. I would be pretty, Spectre's on Mars. I would be pretty psyched about that. They had some initial prototypes. I don't know if they actually went ahead with it. But I wish them the best, and I will go up and take a selfie with them. That'd be awesome. Like I said, I think maybe some of the research that has been done in the wake of our discoveries is a little bit magical thinking, a little bit like, well, we don't know, we should try, maybe something interesting will happen. It's not clear to me that the hat will have unusual or surprising physical properties that outperform other things that are simpler. That's okay. On the other hand, there have also been tons of amazing artistic applications, and of course, in the context of art and design, a little bit of magical thinking goes a long way. So that's great, please bring it on. And so you can see that's a quilt from Emma Lawton. This was sent to me just 2 days ago. It's an artist in Cincinnati who has an exhibition opening this weekend, and just said, hey, I want to show you this. I'm doing these photo collages based on your tiles. So I asked him if I could use it in the talk, because it's very timely. One person, saw the hat, and he worked in a concrete factory, and he was like, I know what I must do, right? He built a giant concrete slab of hat, which is fantastic. This is a microbrewery in Ireland that, bless their hearts, put hats on a beer can, and in fact, sent us some of them to a conference that we held in Oxford. So I have these in my office if anybody wants to wander by. John Paul Wheatley is a pretty amazing soccer ball designer who made a hat soccer ball. This is a low-relief paper sculpture that won an award that was, from there was a hat and Spectre art and design contest in 2023, and I think this was one of the award winners from Cheriton. All right, so that is more or less the story of aperiodic tiles and our discovery of monotiles, and thanks for listening. I think that was about 45 minutes.
Maybe you can entertain a few questions, please, instead.
So I'm kind of lazy, so I don't like to use rules for stuff. I like to just throw things down. Are there aperiodic tiles or shapes that, thanks. Are there aperiodic, apparently that mic doesn't work. I can yell, it's okay.
I can hear you.
Yeah, so
I'll repeat the question.
Are there periodic shapes possibly that don't require so much care and assembly of their?
Right. Are there aperiodic sets where you can sort of vibe it, right? You can like assemble outward and not worry about the risk of getting stuck. Not that I know of. Certainly, like you can make non-periodic stuff, like from 1x2 rectangles. You can just sort of start building out, and it's very hard to actually tile yourself into a corner. But the aperiodic sets we know of, well, yeah, you tend to have to carry some information with you as you go. So you can say, okay, what can I do next at this frontier? It depends a little bit on what else happened and where I am in sort of a hypothetical larger tiling that I'm filling out. There are other ways to manage that process, but ultimately you kind of need, if I placed n tiles, I need like log n bits of information at the frontier to know what to do next.
But to add one more tile or whatever, if you're going to place n tiles, what function of n does it take per time to do it?
Yeah, it's like
Is it exponential?
I think you can place new tiles in constant time with logarithmic information. Well, you know, if you let me carry a bag with a little bit of information, I can always decide deterministically what to do next.
Okay.
Or even sometimes I can hit a point where I can make a decision, a random decision of what to do next. And therefore, I can kind of build I can sample random patches of hats, for example. And Simon Tatham, who has a really good, he's famous for a bunch of things, but including a collection of logic puzzles. He built some logic puzzles based on hats and specters and stuff. And he has some beautiful blog posts that explain how to do this like as a kind of transducer model. Yeah. Over there.
Yeah, I wanted to ask a bit more about the implementation of your software that actually builds onto the tiling. Because I was thinking about like at the start with the hat, Dave gave you this like pretty large tiling.
Yeah.
Like how are you like encoding that into your software? And then how do you? Because like there's like a lot of like.
Yeah, it's a great question.
And how do you like actually like?
So how do you actually do that, right? Well, the first thing that's key, that helps, is the recognition that the hat is like not really a continuous polygon. You don't have to do complicated like epsilons or computational geometry or floating point numbers. What a drag! Everything that happens with hat tilings is constrained to an underlying grid of this shape, of this kite shape, and so it's ultimately a discrete computation. And in fact, it's even better than that, because if you want to fill a large region of the plane with, say, hats, well, it's essentially an exact cover problem for which you can use, say, Knuth's dancing links algorithm. Turns out that's not quite as efficient as you would like. In my code, I use a SAT solver. So I set the whole, the geometry is reduced to a Boolean propositional formula where a satisfying assignment of that tells you exactly which tiles are placed in the patch. Details are in the paper.
And you know you can solve it.
No. I mean, the point of having that software is to know whether a solution exists for any given shape, right? The software is written to sort of handle any shape as input and say, does it tile? Doesn't it
Well,
tile?
SAT solver, I mean, they work on Thursdays.
Oh, SAT. They don't know SAT. It's SAT. They work on Saturdays. Unless they're Jewish, yeah.
So this is a little bit off in another direction. What's the sense of what people have done in 3D rather than?
Oh, yeah, 3D is a great question, yeah. So how does this work in 3D? What's cool is there has been a result in 3D for a lot longer. There's a polyhedron called the Schmidt-Conway-Danzer biprism. It doesn't matter. It's very simple, actually. It's like two triangular prisms stacked on top of each other. And it's easy to show that shape forms first layers, and then the layers are stacked on top of each other, each one rotated by an amount that is incommensurate with 360 degrees. So if each layer is, you're never going to come back to an exact full turn of these layers and get a chunk that tiles periodically. So it is, in some sense, a 3D aperiodic monotile. But mathematicians look at that and they're like, I see what you did, but I'm unhappy about that because if you line the layers up just the right way, you get a sequence of tiles. You get one infinite screw symmetry, like where you could take this layer, turn it and translate it, turn it and translate it, all the way up an infinite line. And that feels too close to comfort for a translation, right? It's too similar to a translational symmetry. It's a little bit off-putting. So the response to that is maybe we want something a little bit more interesting in 3D. And what mathematicians do is, in response is you define a strongly aperiodic monotile in 3D to be a tile that only admits tilings, none of which have an infinite cyclic subgroup in their symmetry group, where infinite cyclic subgroup is like a mild generalization of an infinite stack of translations. It's a more general thing that includes screw motions and other things that only really happen in 3D and not in 2D. And so if you ask for that, that's still open and a good topic for more research. Yeah.
Thank you.
Yeah, that's
Speakers and lunch is offered in the fish bowl next door.
But I'll be around.
Yeah.